Okay, so what I want to do today is I want to continue with applications of probability. And so there's, so many different things we could talk about. And, I've asked a couple of you for suggestions as to what you want to hear about, and so some of you have given me some feedback, which I'll try to work in. I want to also try to recruit a little bit for Small 2014, and talk a little bit about some of the research problems I look at, which you would have more than enough background to understand based on what you've done today. So this is a basically lifted version of a talk I gave last year around this time at Brown, where I was a professor for 4 years, and I taught the mathematical stats class there. So, can anybody recognize, try to hold it so the camera can see, who this is?
It says,
yes. Not everybody's eyesight is good, so you must be very good at the beginning of Spaceballs. So this is Al Capone. I got him from the IRS. Why is the IRS proud of their relationship with Al Capone?
They're the ones who locked him up.
They're the ones who locked him up. For all the stuff he did, it was the IRS at the end of the day that was able to get him for tax evasion. So a couple of years ago, I was a newly minted PhD, and I got an email that began, greetings, my name is David Kelly. I'm a senior criminal investigator at the IRS. And as you can imagine, my head goes down, and my office speaks about, I don't want to talk about it. It's about 5 minutes before I can read the next line of the email, which is, I just read with interest your recent paper in Acta Arithmetica. And I was such a young PhD, the fact that anybody would have read any of my papers, even with interest, just reading them, was quite shocking. And so Benford's law, or Benford's law of digit bias, is used by the Internal Revenue Service and other people. It's a really nice application of basic probability to describe what's going on, and then to prove what's happening in greater detail involves a lot of advanced mathematics. So this lecture is going to serve several purposes. One, it's going to be a great application of what can you do with what you've learned. You don't need advanced theory to make billion-dollar decisions. 2, it is a nice way to review a lot of the material we've done over the semester. 3, it's a great way, as I said, to recruit for Small 2014. And 4, it's a good way to talk a little bit about what math classes might you want to take next. What is a natural progression from this? Okay, so I find the following an interesting question. So imagine you have a nice data set such as the Fibonacci numbers, and you get bored in some other class. And you decide to start writing down the Fibonacci numbers and seeing how often does a Fibonacci number start with 1. And if you just guessed randomly, if you didn't really think about it, go back maybe 5 or 10 years, what percent of the time would you say a Fibonacci number should start with a 1? 10%. 10%. So your first guess is 10%. Then you realize, oh, I had a brain freeze. It can't be 10%. Why not?
Well, it could be. Well, I mean, there's a leading digit for one thing. There's 9 leading digits.
There's 9 possible leading digits. So when we say 10%, we're thinking all the candidates are equally likely. And then we quickly correct, oh, it can't be 10%, it's 11%. Right? Now, this leads to a great stats question. Can you really tell the difference between 10% and 11%? I'm working on a simulation right now for a small project from the last couple of summers. I will have students looking at stuff related to this right now. I'm looking at numbers that have 200,000 digits, and I'm trying to observe some very interesting properties of them. I'm not sure if my students and I have made a mistake between the I want something that's at least this high, or something that's something that is at most this high, or something that is less than this high. Depending on the phrasing you use, you're off by 1. So when we look at the simulations for what the mean is, it's coming in exactly halfway between those 2 interpretations. So unfortunately, it's absolutely no evidence at all of, did we make a mistake in interpreting, I want it to be at least this one, or strictly less than. And so 10%, 11%, can you really see the difference between these in natural data sets? It's going to depend on how much data you have. The actual answer is about 30%. And the first time you see this should be a little surprising. You might think things are following uniformly, things have no bias. This is a pretty strong bias. I will show you later that there's actually no bias if you look at numbers the right way. The right way is going to sound crazy the first time you hear it, but I will try to convince you that this really is a reasonable way to look at numbers. So I'm going to state what Benford's law is, I'll discuss some examples and applications, I'll sketch some of the proofs, and then I'll talk a little bit about some of the open problems. And so I hope some of you will consider applying to small and looking at these and related things over the summer. Okay, So the first thing is a math test indicating fraud is not proof of fraud. Unlikely events can happen. Any college football fans here? Okay, unlikely events can happen. Okay? So here's one of my favorite Dilbert strips based on all the... Oh, I'm going to be very careful since this is being recorded. I'll just say it's one of my favorite Dilbert strips. Your travel expenses are rejected. I don't know why I find that amusing. Because all of your meal costs are round numbers. You're a liar or worse. I decide what to order based on what totals to a round number after a 15% tip. That's worse. So, there could be a natural reason why something looks surprising. So here is Benford's law. For many data sets, the probability of observing a first digit of d base b is about the log base b of d plus 1 over d. So base 10, that means about 30% of the time we're going to have a 1 as our first digit, because the log of 2 base 10 is about 0.3. Okay? So not all data sets satisfy Benford's law. Can somebody give me a data set which does not have this digit bias? You're thinking too hard.
Set of all numbers beginning with 1.
Set of all numbers beginning with 1. Okay. Can I have another one?
What about the integers?
The integers do not satisfy Benford's law. It's a great example. They do satisfy Benford's law if you look at them in another way. What's a number that you might all be getting from me in the near future?
100%.
I'm pretty sure the distribution of our third midterm scores in this class will not satisfy Benford's law. I do not expect 30% of you to have a score starting with a 1. Okay? I'm not expecting that. Batting averages. Temperatures in Williamstown. Right? So, data that's clustered, I don't expect to be Benford. You've got to be able to span a couple of orders of magnitude for there to be a chance of having some kind of bias. So a long street, so this was, Chris's example of the integers is a really good one. So imagine the street goes from 1 to L, and you look at, how many houses have a first digit of 1. Well, if L stops at 199, you've just had 100 consecutive houses with 1. You've got about 5/9 of the houses starting off with a 1. If you end at 999, you've just had a whole string of non-1s. And so the actual answer oscillates between 1/9 and 5/9. So there is no limiting probability. There is a way to rectify this. It uses something called analytic density as opposed to natural density. Natural density is like the claiming Williams. It doesn't discriminate. All integers are equal. The analytic density discriminates. And the integer n is assigned the weight of 1 over n. When you put in analytic density, actually Benford's law exists. And you do have the same bias. And you can even form a bias for the primes. And the primes satisfy Benford's law as well. Now what's interesting is if you take many streets of different lengths and amalgamate them, it's very close to Benford. And this is one of the general principles. The more things you group together, the more things you amalgamate, the more things you average over, the better the resulting distribution. Does this remind you of anything?
Uniform.
Central limit theorem. And we'll actually see that depending on how you look at this, you can see a central limit theorem lurking in the background here. Alright, so here's a lot of different places where Benford's law arises. Recurrence relations, special functions, iterates of maps, products of random variables, that's a big one, number theory, L functions, iterates of the 3x plus 1 map, dynamical systems. How many of you have seen 3x plus 1? I'll talk a little bit about this. If you haven't seen this, you're not really a math major. Right? This is something you need to see. It's one of the things to check off. Difference of order statistics, financial data. This is one of the big reasons why the IRS cares about this, is we believe financial data should satisfy Benford's law. I'm a number theorist. I will show you at least the Riemann zeta function. If you haven't seen this, this is another thing you should see. The zeta function is defined as the sum of 1 over n to the s, where n ranges over all the integers, and it turns out that this is the same as the product over all the primes of 1 minus 1 over p to the s inverse. The proof of this is just unique factorization. Every integer can be written uniquely as a product of prime powers, and the geometric series formula. If you call 1 over p to the s r, I have 1 over 1 minus r, expand that out. This function initially only converges if the real part of s is greater than 1. If you take complex analysis, you find ways to make sense of this in general. In some sense, we're already doing that over here. I have an infinite series, and I've replaced that infinite series with the geometric value 1 over 1 minus r. The Riemann zeta function is extremely important in number theory. We've not talked about this at all in this class, correct? I need 2 volunteers. Okay. What is the next integer after 2013?
2014.
Okay, I need another volunteer. What's the next prime after 2013?
No one's gonna do that.
Okay, so you can see there's a real difference between the two questions. If you're doing any math puzzles or whatnot, especially if you're doing the Putnam, you should know the next prime after 2013. It's 2017. Yeah. Alright, good to know just for those people who are taking the Putnam this Saturday. It's very easy to describe where the integers are. The primes and where they're located is far more mysterious. The idea is to take information about the knowledge of the integers and pass to knowledge of the primes. So for instance, if I take s equals 1, I have the sum of 1 over n. What series is 1 over n? Harmonic. And the harmonic diverges. If there were only finitely many, if there were only finitely many primes, when I put in s equals 1, this would converge. So this proves there are infinitely many primes. There's a lot more you can get out of this. I just wanted to give you one quick example. It turns out the most important value to look at this is s equals 1/2. The celebrated Riemann hypothesis, yes, we do celebrate it, the parties, turns out we believe all the non-trivial zeros of this function, when you extend it, have real part 1/2. And so what I did is I evaluated it at 65,536 points on the critical line. And when we looked at that, here's a plot of how often I got a first digit of 1, 2, 3, 4, 5 compared to Benford's law. I don't remember which one is Benford and which one is the values of the Riemann zeta function. I never bother remembering because they're so close to each other. It is amazing which systems exhibit this bias. It's everywhere. So here are some applications. A lot of them come from computer science, a lot of them come from data integrity. So one, how many of you have read Knuth's books on the art of programming? So he actually has a section in volume 2 where he talks about Benford's law. When you're designing a computer, you want to minimize rounding errors. Where do you want to put your decimal point or your binary point? How do you want to multiply numbers? So Benford's law actually talks about how often you'll have rounding errors. The errors are not uniformly distributed in terms of final digits. Another way is optimal ways in determining how to store numbers. And the one that the IRS cares about and why they contacted me was detecting tax and image fraud, data integrity. So years ago I was watching, not surprisingly, the nightly news, and they had a recap from the Red Sox game at Fenway Park, and then there was a huge controversy the next day. The game was on one network, and another network was rebroadcasting clips on the nightly news, and they edited out the logos for the other network. So they doctored the images. And the network who had paid money for the images to be there was not happy that these images were removed. Can you tell when an image has been modified? So sometimes images are used in court cases. Sometimes images are used for terrorist attacks and other things where people hide messages in images. Can you tell if an image has been doctored? And trust me, there are people who are checking every image possible to see if this has been done. And is there a message hidden in the bits of the image pixels? So Benford's law is a great way to detect stuff like this. And I've done some interesting work with a couple of engineers on this. Alright, so let me get to the general theory. So, a little bit of notation, basically it's scientific notation. I'll say mantissa here. A lot of people say significant instead of mantissa. I'm trying to use the language I think you might have seen. You give me a positive number, and I can write it as it's mantissa times 10 to the k, where k is an integer. So think scientific notation. This number is going to be between 1 and 10, and then that's going to just tell me how many zeros I have before or after the decimal point in terms of padding my number. So two numbers have the same mantissas if and only if they have the same leading digits. And if you think about it, well, if I have the same mantissas, all I differ by is an integer power over here, and that's going to just increase the number of zeros I have or decrease the number of zeros I have. So the key observation is if I want to determine the leading digits of a number, I don't have to study the original number. I can study the logarithm of the number base 10. And more than that, I can actually do mod 1. So what the mod 1 means is I look at this number and I only care about the fractional part. So if you've seen abstract algebra, you understand mod 1 from group theory. If you haven't, Mod 1 just means chop off the integer part, just look at the fractional part of the number. And when you're thinking about the leading digits, this k here doesn't change my leading digits. 0.005 has the same leading digit as 50. And so two numbers have the same leading digits if their logarithms base 10 modulo 1 are the same. So instead of studying my original data set, I can study this transform. And this is a big theme in mathematics, is transforming a data set from one region to another where it's more tractable. Where else have we seen the logarithm being useful this semester in terms of understanding data? I have to put in the understanding data, otherwise there's many places we've seen the logarithm useful. We did this last week, I think on Friday. Where was the logarithm useful for studying data?
To linearize curves.
Excellent, to linearize curves for the method of least squares. Right, when we were looking at the orbits of planets, the data was not great. It was not designed for the method of least squares as given, but by changing variables, we could then use the method of least squares and find the exponents. Alright, so equidistribution. So we say a sequence is equidistributed mod 1 if the probability that it lands in an interval AB tends to B minus A. So implicit in this is that I'm not a moron, that AB lives between 0 and 1. Right? If AB lives in the interval 5, 7, it's never going to happen. So choose some subset of 0, 1 and see what fraction of the time I land it. So I count how many of my indices up to big N live in that interval, divide by the number of indices I've looked at, and in the limit that should go to B minus A. So here's a nice theorem. Professor Silva and I will give you different proofs of this. As an ergodic theorist, he'd prove it one way. As a number theorist, I would prove it another way. This is an extremely useful, powerful theorem. If beta is an irrational number, if it's not in Q, then n beta is equidistributed mod 1. So if you think about this, if I give you beta as a rational number, if beta is 1/4, then if I look at n beta mod 1, I get 1/4, 2/4, 3/4, 4/4, which is the same as 0. 5/4, that's 1/4 again. 6/4, that's 1/2 again. So if I give you a rational number, I just cycle through finitely many values. So no rational number can be equidistributed. It turns out that's it. As long as you know how to rational number, n beta is equidistributed. So if you get bored during the talk, and you can do so discreetly, prove that the log of 2 base 10 and the log of 1 plus root 5 over 2 base 10 are irrational. I think I'll prove one of them. I'll prove this one right now if I remember correctly. So assume that this was a rational number. If it was rational, I could write 2 as 10 to the p over q. And what can I assume about p and q? They're integers. What else can I assume? So I can assume they have no common factors. If they had a common factor of 3, I could remove that common factor. So I'm going to assume p and q are reduced. So if this was rational, I could write 2 as 10 to the p over q. Well, then that means 2 to the q is 10 to the p, or 2 to the q minus p is 5 to the p. So I've got a power of 5 is a power of 2. What is the only way a power of 5 could be a power of 2? 0. So I've got p equals 0 and then q equals 0. Oh, so 2 is 10 to the 0 over 0. Okay, so this means the log of 2 base 10 is irrational. You can also prove with a little bit more work that the golden mean is irrational. Why do you think I care about the golden mean being irrational? Where do you think that's going to come in the talk later? I mentioned Fibonacci numbers. So to understand the Fibonacci numbers, I need to know that the golden mean has an irrational log. Alright, so I'm not good enough, or I'm too lazy to do dynamic slides where I ask you to give me a number and I run the simulations, so I've pre-programmed my 5th favorite irrational number. Okay, my 5th favorite irrational number is the square root of pi. It's a beautiful irrational number. And so what I did is I looked at the first 10 values of n square roots of pi mod 1. And I looked to see how was it distributed in the interval 0, 1. One time I was in the first bin, one time in the second bin. Does this look like it's falling evenly? Does it look like it's falling uniformly? Yeah, and what I like about it, it's not perfect. If it was perfect, you'd think I completely cooked the books. And so there's at least a little bit of fluctuation going on. Right? The fit's not too good. So now here it is for the first 100 values. So about how big are the fluctuations? So here's about 0.9, so it's about 1/10. The square root of 100 is 10. 1/10, yeah, this is about what I would expect. Here's 1,000 values. If you have really good eyesight, here's 10,000 values. So I know you have good eyesight. So at least Andrew can see a little bit of a dip here and here. Okay? The fit is extremely good. So we know the square root of pi is supposed to be, n square roots of pi is supposed to be equidistributed, but it's really equidistributed. The error term is very small, which is going to be very important in a moment. So now it's ready for the fundamental equivalence for Benford's law. So a data set is Benford base B if and only if the logarithms mod 1 are equidistributed. So what this is telling you is there is no bias if you look at numbers the right way. The right way to look at a number is to take its logarithm base 10 and throw away the integer part. Okay? I promise you I will not do this when I'm grading your exams. Alright? There are data sets that you should not do this to, but when you're looking at data sets that span several orders of magnitude, if you really want to study the first digits, what you really want to do is you want to do this kind of transform. The nicest probability distribution we can really think about is the uniform distribution. What this is telling us is there is no bias if you look at things the right way. The right way is on a logarithmic scale, mod 1. And so here's the proof. So here's the interval 0 to 1. Here is the log of 2 base 10. I'm using the change of base formula. When I exponentiate 0, 10 to the 0 is 1. 10 to the 1 is 10. The log of 2 base 10 exponentiates to 2. So every number between 0 and the log of 2 base 10 exponentiates to a number between 1 and 2. All of these numbers exponentiate to a number that has first digit 1. So what's happening is things being uniformly distributed on this scale lead to being biased on this scale. Here I'm evenly distributed, here I'm not. Okay? So this is the fundamental equivalence. This is the way most people prove systems satisfy Benford's law, is they show the logarithms mod 1 are equidistributed. And it turns out the logarithms mod 1 are often very easy to work with. Okay, so let's prove 2 to the n is Benford base 10. Can somebody give me a base where this will not be Benford? Base 2, base 4, base 8. If I choose a base that's a power of 2, I don't expect my leading digits to be uniformly, to follow the correct generalization of Benford's law. And of course, I don't have to look at just the first digit. I could look at the distribution of the entire antecedent. So the proof of this is very straightforward. The log of 2 base 10 is irrational. So if I look at 2 to the n, if that's my xn, so if xn is 2 to the n, yn is n log of 2 base 10. This is irrational. And so since this is irrational, this is equidistributed mod 1, so 2 to the n is Benford. The Fibonacci numbers are Benford. This requires a little bit more work, but we've talked about the Fibonacci numbers through generating functions. It's a nice way to review a lot of what we've seen. And again, this is one of the reasons I'm choosing these topics. It's a way to review the material we've seen throughout the semester without doing the very boring, and now you remember we proved Benet's formula. So I'm basically trying to choose topics over the course of this week to review everything we've done to help you prepare for the third midterm in such a way that it's at least a little bit more interesting. So here's the Fibonacci recurrence. An plus 1 is an plus an minus 1. Here's another way to get to Benet's formula. Guess an is r to the n. So this is the method of divine inspiration. If it works, great. The problem is you can't always count on it to work. So if you guess, you get the formula r to the n plus 1 is r to the n plus r to the n minus 1, or r squared equals r plus 1. The roots are 1 plus or minus root 5 over 2, the golden mean. And it turns out if r to the n is a solution, and w to the n is a solution, then any linear combination of them is a solution. So this is the nice thing about linear recurrence relations. I can add solutions and get a solution. If I have a solution, if I multiply it by a constant, it's still a solution. So the most general solution is going to be of this form. And then when we just take in the first few values, we end up getting this beautiful formula, Benet's formula for the nth term of the Fibonacci. What's nice is this number is less than 1 in absolute value, so when it is very, very large, this is insignificant. So your number is essentially the following. If I take the logarithm the log of a product is the product of the logs. This is going to be a log of 1 over root 5 that's going to just shift everything. So if I was equidistributed before, if I apply a shift, I'm still equidistributed. And now I just need to know, is the log of 1 plus root 5 over 2 irrational? Yes. That's one of the things I told you to think about if you get bored. So the Fibonacci numbers are Benford. You have to do a little bit of work to just prove that this can't change a number that often. And again, if you have a number that's all 9s and this rounds you all up, you've changed the first digit from a 9 to a 1. And so you just have to do a little bit of bookkeeping to show how often are you so close that this will change the leading digit. Most linear recurrence relations are Benford. Now I think we've got 2, maybe 3 people in this class who've taken differential equations. Let me see. Okay, 3, or 2.5. Difference equations like this are discrete forms of differential equations. So if you think of physics, F equals ma, that's a second order differential equation. Acceleration is the second derivative of position. A lot of things in the world are governed by differential equations or difference equations. This is one of the reasons for the prevalence of Benford's law, is difference equations, for the most part, satisfy Benford. It is not the case that every difference equation satisfies Benford. Here's one that does. an plus 1 equals 2an. Can somebody tell me what sequence this is? So make the first term 1, and what will you get? Powers of 2. If instead of putting a 2, if I put a 10, I get powers of 10. So powers of 2, we've shown earlier, this satisfies Benford's law. Here's one that doesn't. an plus 1 is 2an minus 1. If you take a0 equals a1 equals 1, you get a2 is 2 minus 1 is 1. a3 is 2 minus 1 is 1. So if you take this, every term is 1. If instead you take a0 is 0 and a1 is 1, you actually get an is n. And that's the example we saw earlier today, is not Benford, the long street. What goes wrong? What goes wrong here is if you try to write down the, if you guess an is r to the n, you can solve it as before, but you get r equals 1. So your solution is going to look like 1 to the n. And there's a little bit of work you have to do because you actually have 1 as a repeated root. But 1 to the n is not going to be having exponential growth. And that's, or exponential decay. And that's going to prevent the Benfordness from setting in. So there are some small cases you do have to worry about. Okay, so I'm going to look at powers of 2. We know powers of 2 are Benford. The numbers get big pretty fast. These are not as bad as the 200,000 digit numbers I've been working on the past few days, but they're pretty large. So I'm only going to display the first 30 values, but I'm going to look at the first 60 and I'm going to tabulate. So you're all going to be forensic engineers right now. Do you think, here's the observed probabilities, here's the predicted probabilities. Is Benford's law a good fit or not? And if it is or if it isn't, which number is the most suspicious? Which one do you have the most issue with? Or which one do you have the least issue with? Which one do you want to say, great job? 6? Alright. I will give, I don't know, I would say something actually does a better job than 6. I would say 1 does a better job because I've got so many more data points at 1 than I do at 6. To be agreeing this well, to me, is more impressive. I mean, nothing against 6. You've done a great job. If you remember the Toronto Blue Jays, who did a very bad job with the sabermetrics. If you remember the Tampa Bay Devil Rays, who had this beautiful, exponential decay in their tails. I agree 6 is doing a great job. Who's doing the worst job? Who do you want to question? 8? Okay, how many people say 8? All right, any others that you want to question? 9. Anybody else want to say 9? So why 9 over 8? I think 9, I would choose 9 over 8 as well. To me, it's percentage-wise, this is more away from 0.046 than this is from 0.051. They're both, there's issues. Now, one thing is we don't have that many data points. A good thing to do is not to do it as 9 data points, but to clump it into 3, 3, and 3. And if you do it like that, it's actually pretty close. Because this would then be 0.6, 0.5, 0.4, 8, 0.3, 0.1. Those numbers, if you group them into groups of 3, they're not that far off. So I might be trying to do too many bins with a small number of data points. And this is a big issue in statistics. How many bins can I have based on my data? But so I will say that this is the worst. Does anybody notice anything interesting about the numbers?
The powers of 2.
The powers of 2. We'll edit it out, don't worry. The powers of 2. Anything interesting about the values of these powers of 2? What do you notice when you look? How are you reading the table? Are you reading the table going down? How else could you read the table? Going across. Do you see anything interesting now? So what do you see now? They all start with the same digit. So
the first digit repeats.
The first digit repeats. This is, you know, this is 10 further than this. This is 10 further than that. The first digit is constant. Anybody here computer science? Right. How many megabytes in a gigabyte? 1024. 1024. Anybody here Latin or Greek scholar? Okay. Mega to giga, how much of a factor increase is there? I'm sorry? In the land of Greek or Roman prefixes or suffixes, I don't remember which it is, I don't remember if it's prefix or suffix. I think it's a prefix. Is going from mega to giga, how much of a factor changes it? 1,000. So the issue is 2 to the 10 is not quite 1,000. It's almost 1,000. It's 1024. This is the difference between computer science and classics. Okay? No, the language we use, we go from megabytes to gigabytes. Right? We've adopted this terminology. It's not a factor of 1,000. And sometimes if you look at disks as you're copying large files, it gives you so many megabytes, then all of a sudden it changes to 0.99 gigabytes. There's not 1,000 megabytes in a gigabyte. And this is actually what's responsible for Benford's law. If the 1024 was actually 1,000, then this would be 2, 2,000, 2 million. But because of this extra 24, it slowly accumulates. And it takes a while before any of these numbers actually gets to something new. So the question might be, which one do you think is going to be the first one to jump up and get to a new digit? Any thoughts? I might go. We've got 6, 7. So I might gamble, and maybe it's this one that's going to go first. This one doesn't seem. This one seems to be moving a little bit further and a little bit faster than this one. Eventually, they will start to change, but it takes a while, and so it really takes a while before the Benfordness sets in. So we've talked a little bit about chi-squared values. So we've talked about the chi-squared random variable. So if you have something that's normally distributed, standard normal, it squares a chi-squared with 1 degree of freedom. And if you sum chi-squareds, you get a chi-squared distribution with just more degrees of freedom. So a really good statistic to look at is what's the error. And so what I'm doing is I'm looking at the chi-squared values for alpha to the n and just seeing how equidistributed they are. And I chose 3 numbers. So everybody should know what pi is, everybody should know what e is. Gamma is the Euler-Mascheroni constant. We don't know nearly as much about it as we do about the other 2. We have, and I'm seeing how close they are to Benford. So I have 9 bins, it turns out I have 8 degrees of freedom. I'm expecting chi-squared values of around 8. Maybe around 16 at most if it's pretty bad. Which numbers seems to be having some trouble? Pi. Right? The other ones seem very good, they're very small, they seem to be giving very good fits for Benfordness, but pi seems to be having some issues. Is it at least monotonically going down? No. It starts to get better, gets worse, gets better, getting much better, really happy, and then all of a sudden gets much, much worse. So there must be at least one person who can rattle off digits of pi. Who can rattle off digits of pi? much time there is.
I don't have that many.
That's all right, I do a few more.
Let me just start.
Okay.
3.14159368462795383279502832785433, I think. I don't know, that's where it ended on the wall around my math class.
That's what it is.
There's one of those
3.14.
things around.
Sorry?
3.1415.
I know, I was thinking, you know, is there any M&M that's fractured? My daughter dropped an M&M. We named it the Humpty Dumpty M&M this weekend. Okay, what about pi squared? Who can rattle off digits of pi squared? Pi cubed. It's actually very important because pi squared is very close to 10, and so for a lot of things I've actually had issues with computers. If you write 1 over 2 pi, which occurs in complex analysis, the computer passes this as 1/2 times pi, and your answer is off by a factor of 10. So what I need is not just pi or pi squared, I need to keep looking at powers of pi. And if you look at pi to the 175th power, it's 1.0028 times 10 to the 87. What does this mean? It means every time I increase my n by 175 when I'm looking at powers of pi, I almost return to where I started, padded with 87 zeros. It's even better than powers of 2. You know, 2 to the 10 was, you know, 1024. I was off by, you know, not nearly as much as here. So if you look at this, this is a plot of the log of the chi-squared values just to bring things down. If you notice, you know, the blue is, I think, E, which is pretty good with straightly decaying. The red is what I'm getting from looking at pi. And notice, I come over here, I come down, and then I start going up again. Where do I drop? Around 175. The length of these bumps is really about 175. And notice that I am getting better. These bumps are getting smaller and smaller and smaller in terms of their magnitude. But their length is about 175. And this is due to the fact that pi to the 175 is very close to a power of 10. So in the advanced theory of the subject, this is where number theory comes into play, and this is one of the reasons why I'm interested in problems like this. It's how well can you approximate a power of your irrational number with a power of 10. And this becomes a related question about approximating the log of your number. How irrational is the log of your number? So there's a way to measure the irrationality of a number. And the more irrational you are, the better the approximation to Benford, the faster it sets in. Okay, so what I want to do now is talk a little bit about some real-world applications. If you have really good eyesight, can anybody read the name here? Okay, well, this is being recorded, so we'll stop and not say, you know, who this is. We'll just say they're married to somebody named Hillary, and they're from a small town in Arkansas. One of my colleagues says it's amazing what $300 in the Freedom of Information Act can get you. So this is someone's tax returns from 1989. There are some comments. If you want, by all means, you go to the slides and look at them. Here's another net return from 1992. They have one daughter. So here's a nice example of bank fraud. This is a true story. An audit of a bank revealed a huge spike of numbers. Far more numbers were starting with a specific first digit than expected. What digit do you think it was? Not 1.
9.
Not 9.
2.
Nope.
3.
No.
5.
But you're close. You're close.
4.
4, yes! Starting with 4. Right? There was a huge spike with numbers starting with 4. More than Benford predicted. So they investigated further. And they found that not only was there a lot of numbers that started with 4, but their second digits were also clustered around 1 or 2 numbers. Any thoughts?
4.
No. Yes. 4-8 and 4-9. And most of it was due to one person. So when they, yes?
Do you mean like their account balance?
Not balance. So there was, you know, certain transactions, there were certain quantities this bank was dealing with. This was a credit card company. This bank had a credit card division. And there were a lot of 4-8 and 4-9 entries coming from one person.
Like charges?
Related to charges, yes. What happens if you lose a credit card? Or if your credit card is stolen, what do?
You call it.
You cancel it, you call it in. Okay? If you don't know this, okay, if you've learned nothing else this semester, when your credit card is lost or stolen, Professor Miller advises you. Now, sometimes the banks have gotten very proactive. They've actually canceled my cards for legitimate transactions of mine, which were out of character. So I had spent a couple $1,000s for some hotels in Tokyo for a trip I was taking with some undergrads. And rather than calling me and asking me if I meant to do this, they just canceled my credit card. Another time, though, they noticed a couple of charges at Walmart in Georgia for $100, $200 exactly. And they just immediately put a hold on that. And so it's amazing what software the banks have now to look for suspicious activity. So if you lose a credit card, if it's stolen, you call the bank cancels it, are you liable for the charges? It's a wonderful world, right? Now, you're the bank. What do? Somebody's just put charges on the credit card. You have to pay for these charges. What do you do as the bank? I'm sorry? Okay. How much is it worth it to you to figure out who it is?
Depends on how much money.
Depends on how much. If it's $200, do you really want to spend time investigating?
No.
If it's $55,000.
More likely.
So you have a threshold. Any credit card that's reported stolen, if the threshold is below, I'm sorry, if the amount is below the key threshold, you just write it off. If you've seen the Seinfeld episode where Kramer explains to Jerry what a write-off is, you just write it off. Anybody want to guess what the write-off is for the bank?
50.
50 what?
Or
No, 50,000. 5,000. 5,000. Anything below 5,000, the bank doesn't bother investigating. What happened is one of their workers was having their friends get credit cards from the bank. And they would run up $4,800, $4,900, and then they would call. And then if their friend didn't pick up the phone, they would just say, I just want to check my balance or something. And then when they got their friend, the operator, I want to report my credit card stolen. Oh, I'm so sorry to hear that. I'm canceling your credit card right now. Don't worry, you're not liable for the charges. And so they caught the guy using Benford's law. So it's a really nice application of basic probability. People don't know how to create fraudulent data sets. So anyways, in terms of what you've gotten out of the semester, so the write-off limit was $5,000.
So now
So
we know
we
just
know-
do $9.99 and you're...
well, 30% of them.
30%.
Yes.
Start with 1.
So no, a lot of people cluster the numbers around 5. They think it's not so suspicious, or they try to spread it out uniformly from 1 to 9. Cluster around 1,200. Here's a nice example of streamflow data. The person I worked on with this, he's actually a professor of accounting. I'm a professor of mathematics, so of course we write a paper in geology. So we're looking at streamflow data from the past 130 years. The reason is there hasn't been that much advances in measuring streamflow data. The data is very good. It goes back very far. We're looking at the first 2 digits. You see a beautiful fit with Benford's law. Lots of other things. Iran's 2009 presidential elections. There was some analysis as to whether or not those were suspicious or not. What I want to do is I'm going to skip products of random variables. Maybe I'll talk a little bit about them at the end if people are interested. I'm going to just go directly to the 3x plus 1 problem. Just because if you've never seen the 3x plus 1 problem, it's worth seeing. This is also one of the reasons why you should use Darmstadt as your city class if you're ever doing anything in Beamer, because it's very easy with the docs to just jump to any part of your presentation. So, how many of you, I think there was only one hand, have heard of the 3x plus 1 problem? I'm sorry?
I might have heard of it.
Okay, my 2 favorite quotes of it, one is due to Erdős, who said mathematics is not yet ready for problems like this.
Oh, I think I've heard that.
And the other one is by Kakatani, who basically said, when he was a professor at Yale, he would travel around to the country, and whenever he went somewhere, he would introduce people to this problem, and they'd work on it for a month and then give up in frustration. And it led to the quote of people basically saying that this was a Soviet conspiracy to slow down American mathematics. They had deliberately set this problem into us. Any Star Trek Next Generation fans? One of the episode in terms of how they decided to attack the Borg. So there's 2 ways to describe the map. So if I give you an integer x, positive integer, I multiply by 3 and add 1, and then I remove as many powers of 2 as possible. So one way is I do this all in one step. The other thing I can do is I can define it as first, if it's odd, I multiply by 3 and add 1, then if it's even, I pull out a power of 2. So somebody give me a random number.
10.
83.
Oh,
10?
odd. 11.
11. Okay. So I'll do 7.
Okay.
7 times 3, I can do 7 because I know immediately it's going to iterate to your number.
Yes.
Alright, 7 times 3 is 21, pull out, add 1, 22, pull out the highest power of 2, I get 11. I'm going to put a 1 over here to remind myself I pulled out 1 power of 2. I iterate 11, I get to 17. 11, 1, 2, 34, divided by 2 is 17. 13, 5, 1, 1. And once I get to 1, I just keep cycling. If you want a really good number to start with is 27. If you have a really boring class later today, start with 27 just to see what happens. It's fun, trust me. What would you conjecture based on one data point? All numbers will eventually fall into this cycle of 1, 1, 1, 1, 1, 1, 1. So when I'm looking at Benfordness, for this, I don't expect the chain to be Benford in perpetuity because, well, eventually it's going to be all 1s if my conjecture is true. But I could say, well, what happens as I go all the way down to 1? What's the distribution of those digits? Is that going to be Benford? And so we're going to call this numbers here the M path. So the 2 path is just the first 2 terms. The 5 path is the first 5 terms. It's how many powers of 2 I pull out. And so the M path is just which powers of 2 I pull out. So you can ask a lot of questions about the 3x plus 1 problem. It's one of the hottest problems in mathematics. It turns out it's related to incredible numbers of rich, difficult problems. I'm going to skip the heuristic proof of the 3x plus 1 conjecture and just get to the Benfordness. So I want to look at how often, I'm going to just start with odd numbers that are congruent to 1 or 5 mod 6, how often I land in some set A divided by how many numbers there are. Take the limit. Turns out this can all be made rigorous and well defined. If you give me an M tuple, I can ask which numbers have this as their chain. So if I want to know which numbers do I start off by pulling out 5 powers of 2 in my first try, 3 powers of 2 in my second, 1 power in my third, 4 powers in my fourth, it turns out it's given by an arithmetic progression. And we can even compute what Q is, and it starts immediately. And so it turns out that this M tuple in the limit looks like it's M independent, identically distributed, discrete geometric random variables. These are discrete variables we've seen. It's like flipping a coin in terms of weighting. How often do you get the value of 1, 2, 3, 4, 5? And so if I want to look at what is the probability of Benfordness, there's a lot of ways to interpret it. In the interest of time, I'm going to do an easy way. It turns out that xm is going to be where I expect to be after m iterations. So xm is where I am after m iterations. This is where I expect to be. If you do some nice analysis using expected values, you can predict where you think you'll be. This is a ratio of where you are to where you think you'll be. And it turns out this is Benford. And the way you prove this is given by the behavior of a geometric random variable. And then we need to understand this geometric random variable. We have tools that we can do this from probability. So in terms of just trying to briefly conclude, jumping back over here, so we can develop more sophisticated tests for Benfordness. I actually have a test for tax fraud that the IRS has been sitting on for a couple of years. And so I've promised not to publish, and I would much rather have the IRS use this and have friends at the IRS than get one more math publication. But a real area of research is how many data points do you need before you can be convinced that something is going on. You can study digits of other systems. And so I've had a lot of students recently looking at fragmentation problems from physics, where if you break something into decomposable pieces, what can you say about the underlying distributions? So I hope you got out of this some of the applications of what you can do with the techniques we've been learning this semester. There's a lot of really good problems. There's a lot of good math that's connected to. All right, in terms of homework, there's only one homework problem